Welcome to my data science project. My name is Rob van Heij. A few years ago, Eindhoven in the Netherlands started to do air quality measurements. They have some 40 devices installed now, and they take real-time data every 10 minutes. We have temperature, humidity, dust particles in various sizes, and other things. Complete data has been available since 2016. And I thought, because I live in the area, I thought it would be an interesting idea to do some data science experiments with this data. My objective is to use the weather forecast and predict the pollution levels in the city. Pollution levels are most likely affected by weather conditions, and we have hourly forecast available. The most obvious data source for this project is of course the air pollution data. We have 3 years available with 10-minute data samples. I started to explore that in Jupyter notebooks using IBM Watson Studio, and quickly learned that the quality just isn't enough to do what I wanted to do and use the 10-minute samples as is. So I ended up doing hourly averages over all the stations in the city of Eindhoven. That provides more reliable data and takes away some of the quality issues. The other part I used is historical data from the Dutch Meteorological Institute. It's hourly data from one of the stations near Eindhoven, providing temperature, humidity, rain, wind, sun, air pressure, and these kind of features. And I also created some additional features that represent the patterns in human activity, like the day of the year, the day of the week, and the local time in the city. As I mentioned, my objective was to predict air pollution in the city using the weather forecast. The reason for that is that you have a detailed weather forecast available for a few days, and weather conditions most likely affect air pollution in different ways. For example, rain will wash out pollution out of the air, but a rainy day would also encourage people to take the car to work rather than drive the bike. Similar, wind could blow pollution away out of the city, but it also can blow industrial pollution into the city. The complexity of these effects makes it ideal to do a machine learning project with the data. When you're able to predict the air pollution levels, it actually has practical value. You could, for example, warn citizens with health issues when high pollution levels are expected. But you could also consider to automatically adjust traffic lights and change the flow of traffic through the city depending on the expected pollution levels. Or you could work with the airport and have them change flight patterns for the flights leaving the airport when pollution levels are a reason to do so. Finally, if you plan to make changes in the city, like rerouting traffic or closing down roads, you could actually use a model like this to see whether the actual levels of pollution after the change correspond to the model and whether you made a difference by doing this. Before I share the conclusion of my project, I would like to shed some more light on the work that I did. I mentioned my objective, but actually initially I was going to do something completely different. My idea was to use just the historical data to answer some interesting questions that you have when you live in the area. I wanted to observe the flow of pollution over the cities using a 2D convolutional network and determine whether changes to the infrastructure, like for example closing down one of the roads, had actually improved the air quality. As I mentioned, it turned out that the quality of the data just isn't sufficient for such a study. It isn't really accurate. A lot of these measurements are just 10% accuracy. There are a lot of samples missing, and stations are really too close together in the city to do something interesting when you only have 10-minute samples. Also very disappointed was that one of the stations was removed from the place where the roads were changed, so I had no way to do a before and after comparison either. So that's why I revised my objective and decided to use the weather forecast to predict the pollution levels instead. The 10-minute data samples are easy to handle in Jupyter notebooks using Pandas in IBM Watson Studio. Pandas has a lot of support for time series data, and that's what we're working with here. So you can resample, compute averages, and things like that. The quality issues that I have is that pollution levels turn out to be integer values in the range of 1 to 10, which makes them only 10% accurate. There are a lot of readings just completely out of range, and there's also a lot of data missing. Most peculiar was that during the summertime, 1 hour of data is missing every day. Apparently, this is part of the daylight savings change, and I mean, there's no reason why it should be missing, but you see on the chart that I was missing sometimes an entire day, but at least 1 hour a day. So I decided to reduce the data to hourly averages for all stations combined in the city. I excluded the excessive values by comparing the readings between the stations and ended up with an hourly average over all the stations. Data preparation took quite a while to do. So missing data was provided as zeros, which is very awkward when you want to compute averages. So I changed that all to not available, so it can be excluded when you average out. With the small number of samples, like 24 or 30 devices measuring something, outliers have a large effect on the computed mean value. Because the range of the valid measurements is pretty large, you cannot just do clipping. So I ended up doing a per sample comparison between all active stations. You compute a median and standard deviation and use that to remove the outliers. And as you see in the charts below, the before and after shows that the initial awkward distribution has changed into something much more elegant. I started to create a model in IBM Watson Studio with Keras and TensorFlow, training it with 25,000 samples and 20 features. It turned out to be time consuming to train, and it was really slowing me down. So I decided to implement random forest regression to pick the most interesting features from my collection. When I take the features that make up 95% of the influence, I had a prediction that had a mean percentual error of some 10%, which is fairly reasonable, I think. The features I ended up using are the overall date from the start, the number of the day within the year, so that means you have annual cycles and things like that, the average temperature during that hour, the direction of the winds, the day of the week, the time of the day, and the speed of the wind. Interesting that direction of the wind is more significant than the wind speed. Most likely, wind speeds don't vary that much. I decided to do a two-layer model in Keras and TensorFlow. I played around with 1D convolutional networks to learn time series, but those appear to be less effective. Reading about prediction of time series, people suggest that you use LSTM layers as they are the most promising to learn time series. So I decided to do that, training with my 80% of samples and testing with the remainder. My initial experiments were simply by scoring the test samples. And it's funny to see that even after just a few epochs, the patterns already show, and you see the red line in the chart, already learning some of the features but not getting very close. with more epochs, you get much closer to that line. I experimented with varying the number of units in my model and the number of time steps in my samples. The model that you have here will predict 1 hour of air pollution data based on the previous hours of data. And the model I ended up with as the most effective one is 240 and 72 units in the layers. I did the evaluation of my models using the accuracy of a 7-day walk forward prediction. The 7-day walk forward isn't the same as just the next hour prediction. Turns out that a significant parameter is the number of time steps that you have in each sample. There's something like a magic number in the middle, because doing too many or too few time steps both appear to cause it to learn the past rather than the future. So the model will just run behind and will predict the level of the previous hours. I ended up using 23 time steps because that is what the online weather history data from the Weather Channel is. Making the LSTM model much bigger doesn't seem to improve things a lot. If you want to have an LSTM model that will actually learn annual patterns, you would have something like 360 neurons in your layer. And I think that we probably don't have enough history data to actually train all the weight factors in such a model. And having many more time steps in a sample doesn't improve prediction at all. My impression is that when you have more time steps in a sample, you can do with less neurons in your layer to get the same level of accuracy. It's also interesting to see that if you really do far fewer time steps, like 2 hours or so, you miss the more extreme values in the curve. So my conclusion is that with this fairly small neural network, using samples that have 23 time steps, I get a pretty accurate prediction. With the 3 years of historical data, my 3-day prediction is within 5% deviation. And I think that is fairly reasonable, especially when you realize that weather forecast isn't that accurate either. So you cannot tune this much more. And also you cannot predict everything in the world. For example, New Year's Eve, where the Dutch have their fireworks. In the chart you see that just after midnight, well actually that is UTC 2300, air pollution levels go up by a factor of 100 or more. And there's no way you can predict this from just a few years of data. I would like to share some lessons learned with you as well. Doing a project like this from start to end is really a great way to learn things. But when you do, prepare to start all over again and rewrite your code several times, just like I did. Jupyter notebooks are really cool to keep track of what you did and reuse what you've already completed. And when you iterate through this process, keep your iterations really short and review as soon as you can. That way you avoid wasting time to engineer features that you don't use at all, like I did in a few cases, and also validate any assumptions about your data sources, because you can waste a lot of time with data quality issues. Try things with small samples so you can manually verify the results, and with larger data sets, use some charts to validate your results. That really saves a lot of time, because you can train a model forever trying to get a fixed line in it. When you're using IBM Watson Studio Lite, the free trial plan, design and validate your code initially using the free small compute environment. That way you don't burn up your 50 capacity hours. When you scale up, also invest in writing efficient code. I found that I could speed up some factorization code with a factor of 100, and that really helps. When you finally are ready to train your model, do take advantage of the 50 capacity unit hours per month that you get, so you have faster training runs. And I hope you will enjoy doing your project as much as I did mine. Thank you.